Hello and welcome everybody. This is again the MATLAB and Simulink Racing Lounge. In today's episode we are going to talk how you can bring your control model to your race car in 5 minutes. And for that episode I'm really glad to have again guests on board. Hello Daniel, hello Tom, representing the Formula Student Team Delft.
Hello.
Hello.
Perfect, thanks to have you on board. Could you introduce yourself briefly?
Yeah, my name is Daniel. I'm for the .15. I'm the Chief Vehicle Dynamics and Chief Aerodynamics.
Mm-hmm.
I'm Tom. I'm with our team's Vehicle Dynamics department, and I developed the control system for the DUT15.
Okay, control system is the right keyword. So I will briefly talk you through the agenda of today's episode. First, we will hear some news about the Formula Student Team in Delft, about the team and the car. Then we will talk about the controller design process. And then I'm really happy to have 2 software demonstrations in that episode. In one we will talk about the URED controller, and in the other one we will talk about the code generation. Furthermore, we will talk how you guys interface your Simulink models to your engine control unit. And last but not least, as any time, we will talk about the key takeaways. This is the point where I'm handing it over to you. So Daniel, at that point, the stage is yours.
Yeah, so a bit about the team. We started in 2001 with the first competition, FSUK in 2001. Currently, we're building a 4-wheel drive electric race car. Last year, we built a DUT14, which you can see on the right side. It featured self-developed tires, spokeless rim, and improved aerodynamics. And especially the tires and the entire inner wheel drew a lot of attention during the competition.
Okay, this is exactly what most of us have seen last year during Formula Student Germany and Formula Student UK, for example. So very small wheels, and even more, the motors have been attached to the wheels directly. So quite impressive approach.
Yeah.
So do you stick to the same concept also for the current race car?
Yeah, for the DUT15 we have a very similar concept. There's a lot of design refinement, I guess you could say. A lot of weight we lost in the entire inner wheel construction. Some better load pass, some smaller dimensions here and there. But in general, it's the same concept.
Okay.
Next to that, we also have a one-piece monocoque this year. In previous years, we've always glued the top and the bottom half together. Right now, we're building one complete one.
Okay, is the monocoque ready right now?
Yeah. It's finished.
So we are recording the episode in the mid of March, and well, good news that your monocoque is ready to race.
Yeah, we're currently sending it to the painter to get its paint job, and then all the assemblies onto it will start.
Okay, cool.
And then finally, we've decided to mount our front wing and rear wing on the unsprung masses, so on the inner wheels. And this also has proven quite challenging, but still we think it's worth it.
Okay.
And then basically about the electronics, all low voltage electronics are self-developed, include control system, battery management, and ECU. And this basically means that we don't only develop the software, but also the hardware.
Okay, well that's impressive, and really looking forward to hear something about that approach in the next few minutes.
So about the vehicle controls, because that's what we want to talk about. The main goal is improved drivability and performance. We want to help the driver perform on the limit of the car. Because of these control systems, the driver doesn't have to worry about is he applying the right amount of throttle, or is he applying the right amount of braking or cornering or whatever. The control systems in generally sorts everything out. Whatever the driver wants the car to do, it does. And we do that with yaw rate and torque vectoring control for cornering, but also straight line acceleration, includes slip rate and launch control. Finally, we have to employ a power limit set by the rules of 80 kilowatts. This is also something that we control. Of course, we don't want to lose unnecessary power, so we control how much power we output.
Okay, perfect. So what I read here, you have pretty much controllers, yaw rate, torque vectoring, slip rate, and launch control. So really, I'm curious how they interact, Because I assume that none of the controllers can really stand alone.
Yeah, exactly. I think Tom will be happy to answer any questions or
Perfect.
what we do.
Perfect.
Indeed. So let me first tell you something about the way we developed the controller. Our main approach here was to keep it as simple as possible. So instead of having one very big integrated control system, we split it up in main functions. So for instance, we want to maximize the accelerations. And for this we have torque vectoring control, which spreads the torque over all the 4 wheels. We want to maintain grip, for which we have slip ratio control. So these are for longitudinal acceleration, but we also want to improve the performance of the car in corners. And for this we have yaw rate control. This does 2 things. First of all, it increases the angular acceleration of the car, and it also makes sure that the car remains neutral steer.
Okay, perfect. So what we are seeing here on that slide, a single track model, so very basic and simple model that can be used to model your vehicle. Have you been using that kind of model for all your controllers?
No, it really depends for each component in the controller. Each one uses a different model that's most suitable for what he wants to achieve there. The single track model we use is in the yaw rate control. It's the simplest model that can accurately represent what's going on with the car during a corner.
Okay, makes sense to me here. Thank you.
Okay, so here is an overview of the actual control system. On the left is our state estimation, because of course you need to know what's going on with the car. There's 3 main components here. There's a tire load estimation to estimate the amount of grip that we have. There's a speed estimation to measure the speed of the car. And finally there's an EDIF, which calculates the speed of each individual wheel.
Okay, before moving on, let me just wrap up on that. The inputs to your system is basically what you've just said. It's the tire load estimation, the speed estimation. Then it's the driver input, so you call it throttle and brake mapping.
Yes.
Is that correct, or are there any other inputs?
No, these are the main inputs.
Okay, perfect. Well, in the output, as obvious on the very right, it's the motor controllers which send the power or the torque, let's say the current to the 4 motors.
Yes.
Perfect. Okay.
So on the right is the actual control system. And then here you can also see the yaw rate controller, the torque vectoring and the slip ratio that I mentioned earlier. And indeed to the motor controller we send torque limits and a wheel speed set point. And the motor controller then has its own control loop to actually send current to the motors.
Okay, cool. So let me ask another question at that point. So I'm a bit curious about the tire load estimation and speed estimation. So how actually are you doing that?
For the tire load estimation, we are running a full car model in the simulation. Which we compare to measurements from damper travel and from the accelerometers. And based on the movements of the car, we can estimate the load on the tires.
Okay, so what kind of model are you running on your ECU then?
Well, it's a full car model, so that means that we have a chassis body which can move vertically, and it can pitch and it can roll. And then there's 4 bodies for each wheel which can move vertically.
Okay, so also a pretty simple model, but it perfectly helps for the tire load estimation.
Yes.
Okay. Then coming to the speed estimation, are you actually measuring the wheel speeds, or what are you doing when you want to estimate speed?
Well, for the speed we actually use several different methods at the same time. So indeed we look at the wheel speeds, which we also correct for the distance from the COG and steering angles and such. But apart from that we are also having an optical speed sensor which looks at the road and sees
Okay.
the car is actually moving.
Mm-hmm.
And finally, we also have accelerometers, which we integrate to again estimate the velocity.
Mm-hmm.
So we have 3 different methods.
Okay.
And at the end, we combine these measurements using a Kalman filter to get one really accurate estimate of the velocity.
Okay, got it. Perfect. Thank you.
Okay, so that's the overview of the controller. What we want to show today is the yaw rate controller of the car. So let me switch over to Simulink. Okay, so here you can see a very wide overview of our control system. At the top are the car maker blocks.
Okay.
On the left here are the sensors. So in here are just some car maker blocks to get the throttle signal and the brake position and such.
Okay, Tom, sorry for interrupting you at that point, but here again we have a top team using the IPG Car Maker. For the frequent viewers of the Racing Lounge, the IPG Car Maker should be pretty well known or pretty familiar. So what is the reason why you chose that tool for vehicle modeling at that point?
The reason we chose for CarMake is that it's really easily integrates with Simulink.
Yeah. Okay.
And more in general, we want to have some simulation to really test early, which is really important for fixing problems.
Okay, well, also for me that makes perfect sense. And what I see when talking to Formula Student teams, the IPG Car Maker is pretty commonly used. That's my observation at that point.
Okay, so at the right we also have the outputs of the control system. So in here it's basically just the motors and the wheels. But in the center is the main control system, which is what we're looking at today.
Okay, yep.
So in here you should be able to sort of recognize the overview that I showed earlier.
Yeah, basically what we see is the estimation part and the control part. So this is quite parallel, yep.
So in the estimation is again the tire load estimation and your speed estimation and the EDIF.
Yeah.
And in the control units, well, actually, let's just look inside. Here again, you can see the components that we showed earlier. So there's a yaw rate controller, a throttle and brake mapping, torque vectoring, and a slip ratio control.
Okay, perfect.
And what we want to show today is the yaw rate controller.
Okay.
Let me quickly show you what we did over here. On the left is a MATLAB function block, which calculates the reference yaw rate, so the yaw rate that we want to achieve to have neutral steer.
Okay, so can you briefly explain us what is happening in that function? So just to get a feeling of how you calculate the reference.
Okay, let me show you. So on top here is the calculation of the yaw rate reference. And you can basically find your yaw rate reference using your single track model.
Okay.
So it's really just one equation. And below that there's a calculation of the error in the yaw rate. And then there are some more lines about setting the PID values. And that's it, basically.
Okay, cool.
So that's it for the reference. Then on the right, we have built our own PID controller to control the yaw rate.
Okay.
We've built it from smaller Simulink blocks instead of using just the PID block.
Okay. Well, this would have been exactly my question. Why didn't you use the classic or the built-in PID block? So it would be really interesting to hear your thoughts on that.
Well, it's actually as a result of how the control system works. Because the yaw rate controller, it creates a yaw moment command, which is sent to the torque vectoring, which has to apply it on the wheels. But of course, the friction for your wheels is limited. You can't apply infinite amount of torque on there.
Okay.
Which means that the actual yaw moment on a car is not always as big as the commanded value.
Yeah.
And if you use a PID controller, this is a normal one, this can give you problems with wind-up of your integrator.
Okay.
Usually you would enable anti-wind-up in the PID block, but there it's only it can only use fixed limits.
Okay.
While in our case, of course, the grip, it varies all the time, so a fixed limit is not really realistic.
Yeah.
So that's why we build our own anti-wind-up.
Okay. Well, can you just point us to the position in the model where we can see this manual wind-up?
Sure. And this position, we get an MZ error, so that's the difference between the commanded and the actual yaw moment.
Okay.
We subtract this from the input to the integrator.
Okay, perfect. No, fair enough. Great, thank you.
Okay, so that's it for the yaw rate controller. Now let me show you a simulation in CarMaker.
Okay.
Before we start, before the presentation, we've already run one simulation where the yaw rate control was disabled.
So let me chime in. What kind of maneuver or what kind of track are you modeling here?
Yes, of course. We're driving a skid pad in this simulation.
Okay, perfect.
Okay, so what you can see here on the top left is the motor torque, and they're all fairly close together. There's no yaw rate control at the moment, just some corrections for the tire load.
Okay, so I assume we have 4 curves representing the loads on the 4 tires. Can you comment on which are the front and the rear tires?
The yellow and the purple ones are the front.
Okay.
And specifically the yellow one is on the left, the purple is on the right.
Okay.
And the blue and the red ones are the rear tires.
Okay.
Then in the lower left scope is the commanded yaw rate and the actual yaw rate. And you can see that there's quite a difference there in the steady state corner.
Okay.
And this is caused because our car is slightly understeer.
Okay.
It doesn't turn quickly enough based on the steering angle.
Okay. Got it.
Then finally on the bottom right is an estimation of the understeer coefficient of the car.
Okay.
And again, here you can see that during the constant corners it's slightly above 0, which again indicates that the car is slightly understeered.
Okay, so, well, for the steady state cornering, we see some, understeer happening, but what are the peaks? So, the peaks in that signal here.
The peaks happen when the driver changes direction.
Okay.
When the steering wheel is completely straight, the understeer coefficient is not defined and its value goes to infinity.
Okay, makes perfect sense here. Okay, thanks.
Okay, so what we're going to do now, we've set up the controller to enable the yaw rate control. And now we're going to run a simulation and compare the differences.
Okay, great.
Okay, so we've run the skid pad simulation, and the new results are in the scopes on the screen. And there's quite a visible difference. So in the top left again is the wheel torques, and last time they were all fairly close together, but now there's quite a big difference between the torques on the left wheels and on the right wheels. This is done by the yaw rate controller to actually correct for the understeer that we saw earlier.
Okay, that means there's more torque sent to the outer wheels in order to help cornering.
Yes, so in the first part of the skid pad, the tires on the left receive more torque than those on the right to steer the car more into the corner.
Yep.
And then the second half of the skid pad is of course the other way around, so the tires on the right side receive more torque.
Okay, perfect. And also your reference, yaw rate, and the actual raw rate are in very, very close correlation here.
Indeed, they're almost equal, I'd say.
And well, if we have a look at the steady state cornering, well, the understeer coefficient is 0, so we can assume that almost no understeer is happening, right?
Yes, exactly.
Okay, perfect. Well, this is a pretty impressive demonstration of how a yaw rate controller can actually help your car to behave optimal. What is the time? Can you give an estimate on the time you actually saved by applying that controller?
If we enable the yaw rate controller during a skid pad, it will save a few tenths of a second.
Well, and actually a fraction of a second can make a big impact on that. Right.
Okay, so that's it for the yaw rate demonstration. Now we're going to tell something about the hardware implementation of the controller.
Okay.
So for that, it's back to Daniel.
Perfect. Yeah, so about the hardware implementation, at some point you have the assembly controller written, and then it still has to be somehow transported to the car.
Yeah.
But for it to work, it all needs sensor inputs. So if we look at how the hardware actually works with the software, you can see that from the sensors you go to sensor nodes. And these sensor nodes are basically, I think, around 5 or 6 placed around the car at strategic locations. And they collect the data of the sensors close to them. For example, one in the dashboard, one close to the throttle and the brake, etc.
Okay.
And these then transport all the data they receive from the sensors to the ECU.
Okay, let me ask a question at that point. So what types of sensors do you carry around in your race car?
Yeah, we have quite a few sensors, not only for vehicle dynamics, but the major ones that we use in the control systems are the accelerometers, the gyro, throttle and brake, of course, temper travel sensors. That's the main ones, I guess.
Okay, perfect.
And there's also some safety ones like cell temperature and for the accumulator. And then finally, combined with the sensor nodes are the driver interfaces, because we also use those. We have several knobs placed on the dashboard, and with those we can program those for different parameters that we want to change. For example, the understeer coefficient, we can set one knob to different values of it, and then we can just change the knob if we want more or less understeer or oversteer.
Okay, perfect.
Then finally, this data stream combines in the ECU, which then runs the control systems, and then sends out the commands for the torques and wheel speeds and such to the motor controllers and finally to the motors.
Okay. Perfect. I think this is the time where we have to stress again that the ECU you are using here is completely custom built.
The ECU and the sensor nodes are completely self-designed, both hardware and software.
Okay. Well, the reason for that seems to be clear to me. You want to save weight, and you don't want to carry around extra load just for the microcontrollers.
Yeah, and it's also a very good learning process for the engineers that we have, of course.
Okay. Perfect. So what I'm really interested in now is we have seen the Simulink models. We have seen the workflow for hardware implementation. So what really interests me is how you bring your control algorithms to the ECU.
Yeah, I think we can show you that as well.
Perfect. Great.
Okay. So let me show you how we actually export code from the Simulink.
Yep.
So let's go back to Simulink. Okay, so this is again the Simulink model we showed earlier.
Yep.
Before you export code, you first have to make sure that everything is set up correctly. And to do so, you go to the code menu, C++ code, and you can look at the code generation options. And this will, there are several pages here with all sorts of parameters that you will have to look at and fill in for your control system.
Okay. Well, I really don't think we have to go through that in detail, but what really interests me is how much time did you spend on specifying all that?
We did it in about half an hour. It's not
Okay.
that long, actually.
Okay. Well, and is the workflow in that case straightforward?
Yeah, pretty much. It's possible to look at the code generation options, but there's also another tool in Simulink that I would really suggest you take a look at.
Okay.
So again, under code, C++ code, there's also a button for the code generation advisor,
Yeah.
which is a really useful tool because it gives you a list of recommendations on how to options.
Okay.
Which makes it a lot more clear at what options you really need to look at.
Okay.
And apart from that, it also gave us quite a performance. It really increased the performance of the generated code. Because after the code generation advisor, we did 1 or 2 tweaks on the options.
Yeah.
And it's really decreased our runtime, so it's the Simulink code ran about 3 times faster.
Okay.
Which is quite a huge improvement.
Okay, great to hear that it actually helped you. Well, and speeding up your code with a factor of 2 to 3 is impressive. Yep.
So now to the actual generation of the code. So once you have set up all the options, it's really simple.
Yeah.
We go to the control system, right click. Then again, there's a C++ code menu, and you go to build the subsystem.
Okay.
And then it will start to compile your control system. And now it asks, before it really starts generating code, it does ask you about some of the parameters. For this, we choose to inline them. There's no reason to change them from the software, and having them inlined is really a lot faster. So it's all set up correctly, and then it's really just simply you click build.
Okay.
And then it will generate your code.
Okay, perfect. So how long does the code generation usually take?
It usually takes about 2 to 3 minutes.
Okay, well, because then I understand your 5-minute interval, so you use 2 to 3 minutes to actually generate the code, and then you hand it over to your colleagues that actually bring it onto the ECU, which takes about the same time. Is that correct?
Exactly.
Okay, so what I suggest to do now is just to have a look at the generated code.
Okay, so it is now finished exporting the C++ code, which is in a zip file over here. So let's look at what's inside. Inside the zip file are a number of C++ files.
Yeah.
So there's both the export of the control system plus some additional headers that are used for the Simulink integration in your software.
Okay.
And well, let's look at the actual code for the controller, which is here. So what you can see here is that it has exported quite a large file with C++ code to represent the Simulink model.
Okay, and I think the main takeaway that we have here, or the main learning is, well, there's no need to manually code. I think this is all the controller is quite a complex hierarchy, and I don't want to see the number of lines that we would have to write down manually in case we are not using the code generation workflow.
It would be a huge amount of lines. This file, for instance, this is one of the files, and it's already 3,000 lines long, basically.
Okay. No, perfect. I totally agree with your approach. I think it's pretty impressive, and it's also nicely motivating the code generation workflow. And I think this is the point where we should jump over to the key takeaways. You've summarized some points for me. And what I would like you to do is just to present them and give us some further information about them.
Yeah, so finally, the biggest advice that we can give to any team out there is just start with the basics.
Yeah.
There's no need in getting yourself drowned in all the little things that can maybe influence the car. Just start with a simple 2-track model or 1-track model.
Yeah.
And it really is about 95 to 98% of the performance that you want.
Okay.
Yeah, then we would also suggest that you start testing really early if you are building a controller.
Yeah.
So you can test your controller in Car Maker. What we also did is that we tested it on the old car.
Yeah.
And it really allowed us to start testing around January or February. So some basic functions even earlier.
Yeah.
So there's really no reason to wait until the car is finished to start testing your control system.
Yeah.
So in fact, if you start early, you can already fix most of the mistakes that are in there, so that when your car is finished, you can just put the control system on there and immediately start tuning it and letting the drivers get to know the car and such.
Okay. Well, and the last point became really obvious to me. So from model to racing in less than 5 minutes, because if I have a look at your workflow, code generation, putting it on the ECU, and then you're ready to race. Let me ask a question for that key takeaway. So did you apply it for testing? Because I can imagine if it's just 5 minutes, you can tune and tweak your controller and then send your race car out again, right?
Yeah, we do this quite often, especially with algorithm changes. Maybe refining some filtering, something like that.
Yeah.
It's really easy and it's really fast.
Okay, perfect. So I think this wraps it up in a very nice manner. Extraordinary thanks to you. Thank you for sharing so much of your work, so much sharing of your experience. I really appreciated it.
Yeah,
no
no problem.
Well, thanks a lot again. And looking forward to see you competing at the events in summer. Well, this brings me to the end of today's session. So if you want to have a look at all the MATLAB and Simulink Racing Lounge videos, just go to the dedicated webpage, which is mathworks.com/racinglounge. If you want to get all the information about our Formula Student activities, go to the dedicated MathWorks Formula Student webpage. For Formula Student, for example, a Formula Student Germany example, it's mathworks.com/FSG. And again, and I'm really stressing that here, if you have feedback on that episode, if you like it, if you don't like it, if you also want to feature an episode together with me, let us know via formulastudent@mathworks.com. And for those of you who don't know that already, we have a complimentary Formula Student software offer. You have free access to all the tools we are using here in the Racing Lounge and beyond. And if you do use our software, we would be extremely happy if you put our logo on your car and reports. Thanks for watching and see you next time. Bye bye.